Today's lesson is going to be about rational functions. So the way we want to understand rational functions is we want to start by thinking about a reciprocal function. Okay, so it says right here that the graph of the rational function f at x equals 1 over x is shown at the right. But you might be thinking, wait a second, yesterday I just learned about this same function and it was called a reciprocal function. And they really, well, in this case, they're the same thing. So a reciprocal function means that you've taken something and flipped it upside down. So you've taken x, f at x equals x, and flipped it upside down. So the reciprocal of, let's call it just y for ease, of y equals x is y equals 1 over x. And what do I mean by flipped it upside down? What I mean is that we think of the x, what's on the right-hand side, as being a fraction, right? We can think of anything as a fraction, and of course it would be over 1, and I flip it upside down. So 1 over x is the reciprocal of x. And that's the one that we looked at yesterday, or at least in the last lesson anyway. But we can also think of this as what's called a rational function, because rational means it can be written as a fraction. Remember, we reviewed rational numbers a little bit back, and they were numbers that could be written as fraction. Rational functions can be written as fractions. So that's why you're going to see the word reciprocal function used occasionally, like in the last lesson. But you'll also see the term rational function as well, because they're really the same thing. Because reciprocal functions are almost always written as fractions, and rational functions by definition are fractions. Okay, so just that's a little bit to clear up the naming there. So whether we call it reciprocal or rational, I will call it rational from now on. Here it is. We saw it in the last lesson. F at x equals 1 over x is this funky looking graph here that's in two pieces. It's got a couple of asymptotes. You may remember it's got a vertical asymptote and a horizontal asymptote. The vertical asymptote is on the y-axis. In other words, remember, an asymptote is a line that something gets closer and closer to without ever touching. So that would be the line x equals 0. And the horizontal asymptote would be on the x-axis, because as you can see, the graph gets closer and closer to that as well without ever touching it. So those are the two asymptotes of this rational function. What are some of the features of graphs of rational functions at or near values that are not in their domain? Well, what's not in their domain? The only thing that's not in the domain of this one is x equals 0. X can't equal 0. So another way of thinking about an asymptote is it actually is whatever the asymptote is outside the domain of the function. So since this function can never touch x equals 0, that makes x equals 0 the asymptote. So not all rational functions are like this reciprocal one, though. We can have different ones, like f at x equals 1 over x plus 2. That's a little different. We got this extra plus 2 down here at the bottom, don't we? So if we want to see how they compare, let's go to Desmos. Let me just call it up. And I'll type in, again, I'll just use y instead of f at x. It's quicker to type in. So y equals 1 divided by x plus 2. And you can see on the graph something interesting. It's the exact same shape as y equals 1 over x. I might as well put that one on there as well. Y equals 1 over x. Exact same shape. It's simply been shifted a little bit. The red one has been shifted a little bit to the left compared to the blue one. And otherwise, they appear to be pretty much identical, don't they? So how does what general conclusions can you make about how the denominator affects the graph? Well, it seems to shift it left or right. Although we don't have a lot to go on. What happens, let's see if I can make that be true by changing, let's change the denominator a bit. Instead of making it 2, let's make it a 3 or a 10. Yeah, it definitely seems to be moving it farther to left. What if I made that a minus instead of a plus? Now it's moved it to the right. So yeah, it seems as though the denominator is shifting it left or right. Maybe I'll say horizontally. Okay, write a rational function with a domain of x is a member of the set of real numbers, but x cannot equal 2. So let's go back to this for a second. Let's get rid of this one. What would the vertical asymptote be for this graph, the red one? It would be x. The asymptote would be x equals 10. The domain of this red graph was that x cannot equal 10, right? So this 10 seems to be associated with the bottom of the fraction, the denominator, and so just we take the opposite sign, and that would be what it can't be equal to. So if I want something that's going to not be allowed, we're not allowed to have x equal 2, then I might write y, or f at x, equals 1 over x. And I need a 2 in there, but if I don't want it to be positive 2, it seems like, from what we saw in Desmos, that we needed the opposite sign. So I might want x minus 2. We already saw that x plus 2 that we did up above shifted to the left. So x minus 2 probably shifts it to the right. Now let's check that in Desmos. There we have it. Yeah, it's shifted to the right. We can see that x can't equal 2, or x will not equal 2 in this function. And the reason why, let's even just think about the equation, 1 over x minus 2. If I let x equal 2 in that function, then I'd have 2 minus 2, and I'd have division by 0. So again, that's where the asymptote's coming from, and that's why the sign is the opposite. So describe what happens to the graph at x equals 2. It is undefined. State the range. Well, we saw that it still has the horizontal asymptote on the x-axis, so the range would still be all real numbers except y equals 0. And just to do a quick sketch of it, if I put my asymptote here at 2, then the graph would look something like this. Write an equation of a simplified rational function that has 2 vertical asymptotes at x equals -3 and x equals 2. Well, if we follow the pattern that we've already seen, we would need to have, if I want x to not be able to equal 3, then I should, -3, then I should use the opposite sign. So I should do x plus 3, right? That should give me an asymptote at x equals -3. Let's do that right away, and then we can just add the other one later. But I need to make it -3. So I had to make this a +3 on the bottom to get the asymptote at -3, didn't I? There we go. There's an asymptote at x equals -3. But I also need to get an asymptote at x equals +2. So we know that I can get that if I do x minus 2. Again, the opposite sign And if I want to put them both on there, I want to get asymptotes at both of them, then I would have to put them in brackets and multiply them together like I've shown here. So let's wrap some brackets around this. And x minus 2. And interesting looking graph, isn't it? But we can definitely see that we have those asymptotes that we're looking for. The graph shape has changed now. It's not just the two pieces that we had before, but that's because I've made the denominator more complicated. But I definitely still have those asymptotes at x equals -3 and at x equals +2. So graph the function, describe how the two vertical asymptotes affect the graph. Well, they're affecting the graph by dividing it into 3 sections, aren't they? So the purple line and the green line are just supposed to represent asymptotes. We've got 3 sections of the graph. The graph is the red part. 3 separate sections. So it divides the graph, the asymptotes that is. Divide the graph into 3 sections. State the domain and the range. Well, the domain, again, is anything seems to work. It's all real numbers, except it can't be -3 or +2. And the easiest way to write that is just x cannot equal -3, +2. The range, you may recall, let's take a look, but you may recall still has that horizontal asymptote. It's not touching the x-axis, so it still has that horizontal asymptote on the x-axis. So the range would be all real numbers, except that y is not going to equal 0. And if I want to just draw a quick sketch of this graph, I'll put my asymptotes in first. Notice how we had, let's just take a look. It gets very close to the x-axis on the left and right, and it does get close to the x-axis in the middle section as well, but not quite as close. It's almost like a parabola, but it's not really the same parabola shape. It's not got quite that same U shape, though it is curved at the corners. But it's getting close to the x-axis in each place. So if I wanted to graph it, my best estimate would be let's try again. Something like this. There's my middle section, and here's the other 2 sections, getting closer and closer to all asymptotes without actually touching them. In Desmos, graph y equals x squared minus 4 divided by x minus 2. And graph should say y equals x plus 2. All right, so again, we can graph any of this type of stuff in Desmos. Let's just start all over again. So y equals x squared minus, what was it? 4 over x minus 2. I'm going to need brackets just to help Desmos know where to divide by. So x minus 2. Again, I have to remind myself. Yes. So it was x minus 2 on the bottom, and I just do x plus 2 as my other graph. Y equals x plus 2. Interesting. Y equals x squared minus 4 divided by x minus 2 gave me a straight line. That's not necessarily what I would have expected with such a complicated looking equation, is it? In fact, it's the exact same straight line as y equals x plus 2. Let's consider the reason for that. Create a table of values by hand or by using Desmos. What do you notice happens at x equals 2 for each function? Well, when x equals 2, we don't even need to create a table of values necessarily. When x equals 2, for the one I've highlighted in yellow, I would get 2 squared minus 4. So I'd get 4 minus 4 for the numerator, which is 0, and I'd get 2 minus 2 for the denominator, which also equals 0. I'd have 0 divided by 0. That would be undefined. Whereas when y equals x plus 2, I just have 2 plus 2 would give me 4. So the function y equals x squared minus 4 divided by x minus 2 can be simplified if you remember that x squared minus 4 is a difference of squares, right? This here is a difference of squares, which factors as x plus 2 times x minus 2. And once I do that, then I can reduce, because I can divide the x minus 2 by the x minus 2, and I end up with y equals x plus 2, which gives me the exact same equation as y equals x plus 2. So that's why we have the exact same equation, why the graphs look exactly the same, but we have to be aware that when x equals 2, it's undefined. So I'm not sure if I can... There we go. Just trying to show you if I just try to get it. There we go. At 2, it says undefined, right? So, but anything at 1.99 is fine, 2.01, 2.02, all those numbers would be fine. It skips over 2.01 for some reason, but that would be fine. Anything except 2 is fine. So there actually should be an open circle. Desmos doesn't show it, but there should be an open circle at where x equals 2 to show that it doesn't actually hit that point. But otherwise, it makes that perfectly straight line for the reason that I mentioned when I showed how they factored down. The one in yellow factored down to be exactly the same as y equals x plus 2. So sometimes, the point that we can take away from this is that sometimes if we can reduce a function, like we did here, then it'll look the same as another more simple function. Create your own rational function that has a whole at x equals 4. So I didn't use the word whole, but let me just backtrack for a second. This one has y equals x squared minus 4 over x minus 2 has a whole at x equals 2. Right? That was the number that if I plugged it into that yellow equation, the one I highlighted in yellow, gave me an undefined value. So it's a whole. And again, that's what I was showing on Desmos. It was fine everywhere except for that whole at x equals 2. So now we're being asked to create a rational function that has a whole at x equals 4. What connection needs to exist between the numerator and the denominator for it to have a whole? Well, it's going to have to be something where if I divide by, if x equals 4, there's going to be a problem. So on the bottom, I need to have, in the denominator, I need to have x minus 4. Why? Because if I want to plug x equals 4 in and have it undefined, x minus 4 is going to make that happen. In other words, look at my equation as I've written it so far. If I were to let x equal 4, I would have 4 minus 4, which equals 0, it would be undefined. So I need to have that x minus 4 on the bottom. How am I going to then make it so that it's an actual, something similar to the one above? Well, I could use the old difference of squares, just like I did above, to make it the same idea. So I could have x plus 4 times x minus 4, so that when I cancel out the x minus 4s, I'd still have something left. But if I work backwards and multiply, do FOIL on those two factors in the numerator, then I'd end up with x squared minus 16 over x minus 4. That would give me a whole at positive 4. At least it should. Let's give it a try. So let's just change this. Let's just doctor up this equation for a second. Change that to a 16. And change this to a 4. And again, yeah, it did give me that what looks like a straight line. And if I go to the graph and find where it's equal to 4, you can see 3.9 is all fine. Once I hit 4, it's undefined. But once I go past 4, it's fine again. So it's just at 4 where it's a problem, because that is where the denominator would equal 0. We can't have that, but otherwise, if I were to simplify it down, it would give me a straight line. Create a function that has both a vertical asymptote and a hole. Sketch your own function. I'll leave you to play around with that. Use Desmos, have a little fun with it, and see what you can come up with. The rational function h at x equals 1 over x has a horizontal asymptote at y equals 0. Can you create a function that will have a horizontal asymptote at y equals 2? Well, we already saw that adding numbers to the denominator shifted things horizontally. So we might think that we could just add things to the numerator to shift them vertically. Let's give it a try. So let's just start with 1 divided by x. The problem is, if I add something to the numerator, since the numerator is only 1, all I'd end up with is a bigger numerator. It doesn't seem to do anything to shift it horizontally, does it? No matter how much or vertically, no matter what I add, it doesn't seem to be moving it up. I still have my horizontal asymptote at the x-axis. So that didn't seem to work. So what will work? What about if I add or subtract something not inside the fraction? That seems to work. That seems to move the whole thing up, doesn't it? So it's like our k value when we were talking about quadratics in the past. That's going to be a vertical shift, but we have to add it after the fraction, or subtract it if I want to move down. So, can you create a function with a horizontal asymptote at y equals 2? Sure, now I know how. It would be y equals 1 over x plus 2, and that would move it up. Can you write an equation of a rational function without any holes, vertical asymptotes, or horizontal asymptotes? No holes, no vertical asymptotes, no horizontal asymptotes. I can't think of anything off the top of my head. You can play with that one for a bit, and you let me know if you come up with any, though. All right, so as far as the homework goes for today, I want you to just think about these questions and answer them. So just reflect on this. First of all, what determines a rational function? Where a rational function has a hole, where does it have a vertical asymptote? When does a rational function have the horizontal asymptote at y equals 0? When does a rational function have another horizontal line as the horizontal asymptote? We just talked about that one, right? Some rational functions have asymptotes, others have holes, some have both. Explain how you can identify without graphing which graphical feature a rational function will have. And then key ideas and a little bit more practice. Good luck.